So in digital systems, we don't subtract binary numbers, but binary numbers are added. So digital systems have circuits in them that are made out of basic elements and, or, and not. And they perform binary addition. So a half adder is a circuit that performs binary digits on, or binary addition on two digits. The digits we can call A and B. If you're looking this up on the internet and looking at YouTube and everything about half adders, you might see them called X and Y. I'm going to call them A and B here. So a half adder is something that adds two binary digits, A, B, and there are two outputs. The outputs are called sum and carry. Sometimes people call carry the word count, but so we call the outputs S and C. So here we go. Here's a picture of what a half adder is. Right now it's just shown as sort of a box, and the inputs are A, B. A can be a 1 or a 0. B can be a 1 or a 0. The outputs are S and C, sum and carry. Or some people call it sum and count, but S and C are the outputs. So these are inputs, these are outputs. So, outputs. So let's explore what is in here. We can design what is in here from scratch. Let's design a half adder from scratch. Well, we know that these inputs can either be a 1. We know that the inputs can either be a 1 or a 0. So then the inputs are either a 0 or a 1. That means that we have 2 to the n values in a truth table, 2 to the power of 2, which is 4 entries in the truth table. And here I'm showing what all of the values could be that are inputs A and B. So that's our first step of designing a half adder, is seeing what the inputs are. Now we can make a truth table for the outputs. So the inputs, here's the inputs that we just determined above. The outputs are the result of binary addition. And remember that in binary addition, we have to remember that 0 plus 0 is 0, carry 0, and 0 plus 1 is equal to 1, carry 0. 1 plus 0 is equal to 1, carry nothing. And 1 plus 1 does not equal 2, it equals 0, carry 1. So let's do that here. 0 plus 0 is 0, carry nothing. 0 plus 1 is 1, carry nothing. 1 plus 0 is 1, carry nothing. 1 plus 1 is 1, carry 1. So let's analyze this output. Let's look at this. What kind of a oh, sorry, made a mistake. 1 plus 1 is 0, carry 1. So now let's look at this. Now it looks right. What kind of a circuit has this output? What circuit has this output? Well, an OR gate is high. The output is high if one or the other or both are high. So it's not an OR gate. It's not an AND gate, because an AND gate says that the output is high only if all inputs are high. This is, if you remember, exclusive OR. The output is high when exclusively one or the other, but not both, are high. So this is exclusive OR. So therefore, sum, the output sum is A exclusive OR B. So sum is A exclusive OR B. And now let's look at carry. Carry is low unless all outputs are high. Well, what kind of a gate is this? This is clearly an AND gate. One and the other must be high in order to get the output high. So this is just A, B, an AND gate. So carry equals C equals A and B. So now we have designed our circuit, haven't we? Now we know what this circuit looks like. What it looks like is it has a sum that is exclusive OR, and it has a carry that is A and B. So sum equals A exclusive OR B, and carry are the two outputs, A and B. So let's look at carry being A and B. Well, it would be an AND gate, wouldn't it? And A would go in, and B would go in. So there we go. I've satisfied this. I just want consistent color coding. Now, the sum output was an exclusive OR. Exclusive OR with the inputs A, B. So A goes in and B goes in. So this is a half adder. Let's see if we're right. All right, earlier on, I said a half adder looks like this. So carry comes from an AND gate. A and B go into the AND gate, and sum is an exclusive OR of A exclusive OR B. So we have just designed a half adder. To extend this knowledge further, let's say, for example, on a final exam, I could ask you, please make a half adder, but make it with only the basic gates of and, or, and not. Then you would have to replace this exclusive OR with ands, ors, and nots. See if you remember how to do that.